Hello. In this video, I'm going to address why reference angles are positive and acute. Now, I do have another video on how to find reference angles, and in that video there is a nod to the why, but this video is hopefully going to go in a lot more in depth and address certain questions like what if the size of the circle changes, or what about different kinds of angles that seem to have the same reference angle and things like that, and why can I calculate the reference angle seemingly so many different ways. All right, so hopefully we'll answer those questions in this video. All right, so I want to first remind you how we find reference angles, and basically you first find your reference triangle, and it's by dropping a perpendicular line to the x-axis from the point of intersection between the terminal side of the angle and the circle. The reference angle is the angle, the positive and acute angle between the terminal side of the angle and the x-axis. Now that's a lot of verbiage, and I do find that sometimes students have trouble drawing the reference triangle, so and therefore the reference angle. So let's go ahead and do that for every quadrant, okay? So let's say I'm going to go ahead and use a red circle so you can see it. Let's say I'm in quadrant 1 and I rotate a certain amount. I already managed to get myself marked. It's so fast. I rotate a certain amount in the x-axis. I'm sorry, in the positive direction in the first quadrant. All right, and let's say it stops here, the rotation. So here is the point on the circle, right? So what we represent, the terminal side of the angle right here. Here's the point of the circle on the circle. That's the intersection between the terminal side and the circle. And now from this point, I drop a perpendicular line to the x-axis. There you go. Now the reference angle is the angle between the terminal side, was right here, and the x-axis. So it's this rotation right here, that rotation right there. All right, so let's do it for the second quadrant. Now here I'm going to rotate somewhere to the second quadrant, like that. And remember how we represent that is we say, oh, here's where it terminates, right? So it went all this way. And here's the point of intersection between the terminal side of the angle and the circle. Now drop a perpendicular to the x-axis, that. And then the angle itself is right here between the terminal side and the x-axis. This is it, theta, okay? And now let's do third quadrant. And you might want to pause the video and draw it. It's good to develop these skills. Just hearing them is great because you do get at least one sense involved in seeing them, but doing is another sense, and it imprints better. So go ahead and do that. So here's the third quadrant, right? So the idea is I have the terminal side here. Here's the point of intersection between the circle and the terminal side. I drop a perpendicular to the x-axis. And the angle is between the terminal side and the x-axis. It's right here. Okay. And then finally, fourth quadrant, if you want to pause the video. And I'm going to rotate all the way to the fourth quadrant. Remember, I always start from 0, by the way. This is intended to be also. I start from 0, rotate around, and I terminate it here, let's say. So here's my terminal side. Here's the point of intersection of the terminal side and the circle. Drop your perpendicular to the x-axis, and now that forms your reference right triangle. Here is your reference angle. Okay, so that's how we do that. And now let's take a look. What are we trying to say here then? Why is it that we even go through this? Well, the triangles in the first quadrant contain all the information from the triangles in the other 3 quadrants. So for a specific angle, the ratios are the same regardless of the quadrant. The only thing we need to do is adjust the trigonometric ratios sign, S-I-G-N, positive or negative, depending on the quadrant we're in. So that's why we only need to work with the triangles from the first quadrant where all the angles are positive and acute. So in the first quadrant, that's always going to be true. The angles are positive and acute, so they're the reference angles. Now let's take a look at that for a specific angle. Let's take a look so you can see that. So let's say we're on the unit circle where the radius is 1, and let's take an angle 30 degrees. So if this is a 30-degree right triangle, then you know the opposite is a half, the adjacent is square root 3 over 2, and the hypotenuse is 1. So how does this fit onto a circle? So when you standardize it, right, so let's take a look at what happens. All right, so let's say I were to rotate out 30 degrees. So I'm going to say it's something like this. It may not be exact, but something like that. You drop your perpendicular to the x-axis, right? Here's your 30-degree angle. And now what you would know is, oh, okay, across from it is a half. Let me put that in maybe a different color. And here the adjacent square root 3 over 2. And here the hypotenuse is 1. But because we've standardized this, right, the definition is to always drop the perpendicular to the x-axis. Then what will always happen is the adjacent is the x, the opposite is the y, and the hypotenuse is the radius. So now you've got those definitions in terms of r, x, and y, and those will always stay the same for that particular angle. So, well, for all angles, the r, x, and y are the same. So x is the adjacent, y is the opposite, and r is the hypotenuse. All right, so now if you look at this, what happens is if I were to reflect this, just like fold it over and put it on, let's see if I can draw this pretty well here. If I were to reflect this into the second quadrant, then that means that this triangle right here would also have a 30-degree angle between the terminal side and the x-axis. It's the same triangle, so obviously the lengths of the triangle, the sides of the triangle, have to be the same. So this would be square root 3 over 2, except that it's negative, right? Because we're in the second quadrant. And here would be positive a half because we're in the second quadrant. But that means that, and here the radius is the same, but that means that the ratios are going to be the same. And so what angle is this? Well, if this is 30 degrees rotation from the x-axis, right? And here the x-axis value is 180, then this must be what? 150. And we can play the same game over here and reflect this triangle into the third quadrant, right? And if we did that, I'll do my best here. All right, let's say this is the terminal side. We drop the perpendicular to the x-axis, and my apologies, this would of course be exact. And so again, this length of this, the x-coordinate is square root 3 over 2, but it's negative because it's in the third quadrant. And here, for the y-coordinate, it'd be a half, but it would be negative because I'm in the third quadrant. But the lengths are the same, so the ratios are the same. So all you have to do is adjust the sign, S-I-G-N. And again, of course, you could do the same thing. Oh, and let me tell you, what would this be? So this is an angle of 30 degrees beyond 180, so you'll be at 210, right? And we can do the same thing here and reflect this triangle, right? Just flip it down. And here you would have this reference triangle. This triangle, this is a reference triangle, but it's based on here. This angle here is also 30 degrees, so you know this is square root 3 over 2, and this is, for the y value, negative a half because we're in the y in the fourth quadrant. So again, it's because you're reflecting the reference triangle into any other quadrant and all the lengths stay the same, so therefore the ratios would have to stay the same. And all you do is adjust for positive or negative, depending on the quadrant you're in. Okay? So that's what we're talking about. You only have to adjust the trigonometric ratio sign depending on the quadrant you're in. So let's take a look then. Hopefully this makes sense that the ratios would stay the same. Let's take a look at a specific example. How do I use this? Well, suppose you're asked, you're going to be asked tangent of 150. Well, you know tangent of 30, right? We already know that. So here's 30 degrees, right? The x and y coordinate then are square root 3 over 2 and 1/2. You know that the definition of tangent is y over x, so you just place the y over the x. So you take that ratio and you simplify it, and you get square root 3 over 3. So then if you're asked, well, what is tangent 150? You would find the reference triangle and angle for that. So you'd rotate 150, drop the perpendicular to the x-axis, find the difference between the value of the x-axis and your terminal side, the reference of the angle you're given. That difference is 30 degrees. So you know you're using the same information. You've got, you know the sides, the lengths of the sides. This would be negative square root 3 over 2 and positive a half. So now you say, well, the tangent of 150 is defined by the lengths y over x. And in this case, the y coordinate is a half, the x coordinate is negative square root 3 over 2 because you're in the second quadrant and x is negative. But you're still using the same basic information from tangent 30, you're just adjusting it for tangent 150, and you say, oh, well, it's now negative square root 3 over 2. I'm sorry, square root 3 over 3. All right? Now, you may ask, why are there so many ways? Sometimes you may be watching somebody or other students working on reference angles. Why does it seem to be there's so many ways to find a reference angle? So we're going to go through that example. Suppose you were asked to find the reference angle for 626 degrees. So generally, most books will tell you, well, the process for finding a reference angle is to first express that angle, the given angle, as a coterminal angle between 0 and 360, or between 0 radians and 2 pi radians, depending on what system you're in. And then what you do is you subtract the two angles. So using the possible x values of 0, 180, and 360, or 0, pi, and 2 pi, find the positive rotation between the coterminal angle and the x-axis by just subtracting them. All right, so let's take a look at the example. And here you would say, if we follow the rules, right, of first expressing the given angle as a coterminal angle between 0 and 360 and then finding the difference. Let's go ahead and do that between that value and the x-axis value. Let's go ahead and do that. So you're here, you wrap around, and what you find is that you're going to end up in somewhere in quadrant 3, and you're like, well, okay, let's suppose it's here, and you say this is 626, and then you say, okay, let's go ahead and subtract 360, and what you get is 266 degrees. Now, if I were a little more accurate, this is probably going to be a little bit closer out here, so I may have to redraw that. But you're like, okay, what I'm looking for is this rotation between the terminal side of the angle and the x-axis. So what's the nearest x-axis value? Well, it would be 180. So you'd say, oh, okay, well, the difference between here, now I'm going to express this as coterminal of 266, right? So what happened is I started at 0, rotated all the way out to 266, and I want to know what is this rotation between 266 and 180. So I subtract them. And I get 86 degrees. So actually I should be way out here, right? Because 86 degrees is almost out here at 90 degrees past the x-axis, but that's what I represented. So this is actually your answer. The reference angle is 86 degrees. If I were to draw this a little bit more correctly, it would probably be more like this. Drop to the x-axis, right? That'd be more correct now. And this angle in here, right in here, is 86 degrees. And if you were to reflect this, then what you would find is you would be 86 degrees like this, right? This is the reference triangle for it and reference angle. This angle being 86. But the length, this length is the same as this length is the same as that length, and of course the hypotenuse, or the radius, is the same. All you have to adjust for is the positive and negative signs for x and y. So this is one way of figuring it out, but somebody could have said, well, you know what? This is the regular process, but what if I said instead, when I have 626 degrees, I know how to draw this. It's out here somewhere. And then the x-axis value for that would be 540 degrees, right? It'd be 180 plus 1 revolution, 360, is 540. And now I'm just going to say, oh, what's the difference between 626 and 540? Well, of course, you're going to get 86 degrees. That's this rotation in here, okay? That's where you're not changing it into a coterminal angle. You're just working with the angles themselves and saying, okay, what's the nearest x-axis value, and just subtract them, because I understand what I'm doing. I'm finding this rotation right here, okay? And you might have instead been given, instead of 626, you might have been given negative 94 degrees. And guess what? It's another coterminal angle for 626, except you're going in the negative direction, going negative here, just past 90 in here, a little 4 degrees past it, right here. So you're at negative 94 degrees. It's really the same. If you were to say, well, use the process that we were taught by most books to, let me find it again, express the angle as a coterminal angle first, and then find the nearest x-axis value and subtract. You would say, okay, let me add 1 revolution, right? So that would give me, let's see here. What did that give me? Also 266, yeah, of course, the one we started with. So it would give you 266, and again, you do the same thing we did before. The nearest x-axis value is 180, right? And that would give you 86. Or you might have said, well, I went back negative 94 degrees. What if I were to keep going to the x-axis? That would be what? Negative 180 degrees. So, or you could do, what's the difference between negative 180 and negative 94? Put in an absolute value so that it's positive, and you'd get 86 degrees again. Or you could have subtracted the other way, negative 94 degrees minus negative 180, and made it positive. Because again, all you care about is you drop to the x-axis, you care about this rotation between the terminal side and the x-axis. That's all you're looking at. So because there's so many coterminal angles, it kind of really doesn't matter as long as you know how to convert. So I'm just kind of going into this because sometimes students get confused as how is it there's so many ways of finding this. So what books do is they simplify it by saying, well, if you turn everything into a coterminal angle between like 0 and 360, then the x-axis values can only be can be 0, 180, or 360. And so it simplifies it. You don't have as many ways, but a lot of people still use the angle they're given. Right? So that's why there's so many different ways. Now, you may also ask, well, what if the size of the circle changes? How can I know I can still use these reference angles? Well, here's the idea. It really doesn't matter what size circle you have. If my angle is a 30-degree angle, it's the same on every circle. When I drop a perpendicular to the x-axis, these are just similar triangles. And remember, similar triangles all have the same ratios. Not the same lengths, but the same ratios. So it will end up being the same. Here's a specific example. Suppose I had a radius of 5, and we're looking at the 30-degree angle. Well, that means every length is going to be multiplied by 5. So the radius is going to be 5, the y coordinate is going to be 5/2, the x coordinate is going to be 5 square root 3 over 2. So here's your angle, and again, you would just drop to the x-axis. Here's your reference angle, and watch what happens. Here's the definitions of your trig ratios in terms of x, y, and r, but using these longer lengths because your circle is bigger, but everything got proportionately bigger, so the ratios stayed the same. So yes, you can use the reference angles on any size circle. Okay? Thanks so much for listening.